Okay, so we're just now starting chapter 13. So let's put down chapter 13. And let me tell you what we're going to do in this chapter. This chapter will be all about solving the differential equation. So d mu plus m squared phi naught of x is equal to minus I j of x. So it's all about solving this differential equation in detail. So by the time we finish this chapter, you will know exactly how to solve this partial differential equation. Okay. Now, remember this partial differential equation came up in the last chapter. And if we're able to solve this partial differential equation, then we can calculate z of j, the generating functional of time-ordered correlators. So that's why we want to solve it. What is the method that we're going to use to solve it? So we're going to use a specific method. The method is called the Green's function method. This method is very general. So Green's functions are used in electrical engineering, mechanical engineering, in applied mathematics, in physics. So it's well worth discussing this method in a lot of detail and making sure we really understand it very well. It will hold whenever you are dealing with a linear differential operator. So my goal is going to be to really explain this method to you properly so that no matter where you have to use it again in the future, you're going to be able to use it and you're going to understand it. So the first thing that I'd like to understand or like to state, I want to give you a definition. And what I want to define is a linear operator, okay? And if you want to check that if an operator is linear, you would check the following equation. So we've got some operator O hat, and we allow O hat to act on alpha 1 F1 plus alpha 2 F2. O hat could be an ordinary differential operator. It could be, perhaps we're thinking about a differential operator that differentiates with respect to many coordinates, in which case it could be some sort of a partial differential operator. So F1 and F2 here are functions, and they could be functions of a single variable, or they could be functions of many variables, okay? And the variables that we're differentiating with respect to. Alpha 1 and alpha 2, on the other hand, are just constants. You can think of them as real numbers. They're not functions. Well, if the operator O hat is linear, it means that this equation is true. So O hat acting on alpha 1 F1 plus alpha 2 F2 is equal to alpha 1 acting on, with O hat acting on F1 plus alpha 2 with O hat acting on F2. So this is the equation that needs to be obeyed if O hat is a linear operator. And notice something. Okay, so, well, let's start. Let's start. And what I'm going to do is I want to consider a few examples. So let me first look at an example of an O hat that is a linear operator, and then we'll look at an O hat that is not a linear operator. So let's say O hat is equal to, so I'm telling you what O hat is now. It's the f dt plus t squared times by f. So I'm only thinking about an ordinary differential operator. We're differentiating with respect to a single variable, but let me stress that the definition that we've given here would work no matter how many variables we are differentiating with respect to. And now how do we check? So what do we want to check? Is O hat linear? That's the basic question that we're asking now, okay? So we'd like to know, is O hat linear? So what do? Well, we take O hat and we act on alpha 1 F1 plus alpha 2 F2. Well, that's easy. We want d by dt on alpha 1 f1 plus alpha 2 f2. And then we want plus t squared multiplied into alpha 1 f1 plus alpha 2 f2. So let's take the derivative first. Well, the derivative of a sum is the sum of the derivatives. So I can just add the derivatives of those two terms. And then I want to use a second fact, and that is that the derivative of a constant times a function is a constant times the derivative of the function. So using those two rules, we'll get alpha 1 df1 dt plus alpha 2 df2 dt. And then plus, well, for the second term here, we've got t squared multiplied by two things, and you know how to multiply out a bracket. We'll just get alpha 1 t squared f1 plus alpha 2 t squared f2. Okay? And let's sum these two terms. And I'm going to group the terms. There's a term here with an alpha 1, a term here with an alpha 1. So if I sum these two terms, let me take out the alpha 1. I'll have the f1 dt plus t squared f1. Good. So that's the first term. And now I also want to group the two terms that are multiplied by alpha 2. So again, I can take out an alpha 2. And then what do I have? Well, I've got the f2 dt plus t squared f2. Great. Okay, but look at what we've got. This is very easy to identify. The first term is just alpha 1 O hat acting on F1, and the second term is just alpha 2 O hat acting on F2. Well, that's exactly the boxed equation at the top of the page, so we can immediately conclude this is actually a proof that O hat is a linear operator. And I want you to notice something just so that you can build your intuition. Look at what O hat looks like. Okay, let's just make a comment. So this is a linear operator. And notice that each term, so there's two terms there. The first term and the second term are both linear in F. Okay, so that's the connection you should be making. This is actually why O hat is a linear operator. So let me give you a little bit of evidence for that. We should always give evidence for any claim we make. Now we'll do a second example. And for my second example, let me now choose O hat acting on F. We can still keep a df dt, why not? But then let's have plus t squared. And now let's violate this form that every term is linear in F. Let's put here an F squared, okay? So let's check if this is linear, a linear operator or not. So now we can take O hat acting on alpha 1 F1 plus alpha 2 F2. So same logic. So this is again going to be a d by dt of alpha 1 F1 plus alpha 2 F2 plus t squared. And now we've got the square of alpha 1 F1 plus alpha 2 F2. What is this equal to? Well, the first term we've just dealt with. So that one is straightforward. I'm just going to do exactly what I did above. So we get alpha 1 df1 dt plus alpha 2 df2 dt. And then for the second term, I can just multiply out all of the brackets. And what do I get? I get alpha 1 squared, t squared, f1 squared, plus the cross term will be 2, always for the cross term, t squared, alpha 1, alpha 2, f1, f2. And then there's one more term, which is alpha 2 squared, t squared, f2 squared. Okay? So that's O hat acting on alpha 1, f1 plus alpha 2, f2. Now, if this is a linear operator, this should be equal to alpha 1 acting on O hat f1 plus alpha 2 acting on O hat F2. And let's see what this is. Well, this is going to be alpha 1 df1 dt plus t squared f1 squared plus alpha 2 df2 dt plus t squared f2 squared. And what you can see is this is not equal to O hat acting on alpha 1 f1 plus alpha 2 f2. Let's just see that, okay? So let's first of all look at the terms that do match. Well, here we've got an alpha 1 f1 df1 dt, and that matches against this alpha 1 df1 dt. Then sitting over here, we've got an alpha 2 df2 dt, and that'll match against this alpha 2 df2 dt. So those two terms are the same in the two expressions, and notice that this is the piece of O hat that's linear. But now look at the other terms. Well, look, here's an alpha 1 squared. There's no alpha 1 squared down the bottom here. Here's an alpha 2 squared. There's no alpha 2 squared. And here's an alpha 1 alpha 2. Well, there's no alpha 1 alpha 2. So these terms do not match. And notice something. These are all coming from f squared. So this is indeed the piece that's not linear in f, and this is what screws up the linearity of O hat. Okay, so this implies O hat is not a linear operator, and the connection that you should be making for yourself is O hat is not linear in f. And why? Because, well, let's just labor the point. This is linear in f, and this term is quadratic in f. And it's that term that's quadratic in f that spoiled the linearity of O hat. Good. Okay, so why don't you dream up some operators and see if you think they're linear or not, and then check it, okay? That would be a good exercise to make sure that you've really mastered this. I want to end this little segment with a note, an important note. So here's a note. Note, O hat acting on phi naught of t and x, and by O hat here, we mean d mu plus m squared phi naught of t and x. And let's even just be as explicit as we can. This means two time derivatives. So now we've got many variables and many derivatives, which means we're dealing with a partial differential operator plus m squared phi naught of t and x. This is a linear operator. So please check that. You should know enough to do that. So what should you do? Well, you should allow O hat to act on alpha 1 phi 1 plus alpha 2 phi 2, and just check that this operator is a linear operator, okay? So it is a linear operator, and that means we can solve it with the Green's function method. Okay, so now let's move on. Let's discuss actually what the Green's function method is.